Hello, everyone. Let's continue our lectures, and this is the last lectures on Python programming for solving nonlinear program. The topic we're going to talk about today is the so-called least square model. The least square model was originally using for regression type of applications, and I just want to using a one Jupyter notebook to introduce these least square model can be applied for many different applications. Of course, the least square model can be applied to solving, finding the minima of a objective functions, like a regular minimization problem with a non-constraint or constraint. And second application for the least square I would like to demonstrate, and least square problem can be used to solve a system of linear or nonlinear equations, and especially with some sparse matrices. The third application I would like to introduce is using the least square problem to do the curve fitting, which is the original intent for the least square algorithm and least square models. So we'd like to introduce these three different applications. So show you least square models. Actually, they just try to minimize a summation of a function, square function, and then we call these residual functions. However, the application of the least square algorithm can be utilized in many different aspects, and the algorithm scipy.optimization library provides for showing very stable and reliable convergences for solving these type of model. So many times I would even prefer to using the least square model instead of the classic minimization model as well. So let's introduce the first application. It's like a regular minimization subroutine scipy.optimize provides, trying to find the minima of a particular function. Again, what we use is using the Rosenberg function like we tested before, and we're trying to show you how to remodel this function of Rosenberg functions over here in equation 1 and 2. Equation 1 is the two-dimensional version of the Rosenberg function. Rosenberg function can be expanded to n dimension and can be generalized. And equation 2 is the first derivative of these two-dimensional version of a Rosenberg function. What I'm trying to do is the least square models and minimize the residual function in the following form. Actually, is minimize summation of a particular function we call Ri. Ri is a function of x. Ri squared, which is minimizing the sum of square. It just happens to be, if you can see in the equation 1, actually, there are two terms in this Rosenberg function, and both of them are in the square format. So we can easily adopt this function into so-called residual function form of Ri of x squared. The first one is, so the r of x, so function r, is a first square is 10 times x1 minus x2 squared, and that's the first term. Second term is 1 minus x2 squared, so this is the second term. So instead of using the original functional form, we're using this residual vector, okay? But we know the least square function is trying to minimize their sum of their square, the first term and the second term. And also, based on this, I can calculate the so-called Jacobian matrix respect to the residual function R. So this will simplify quite a bit of the how we present the Rosenbrock function. So basically what we do is we give you a definition of the Rosenbrock function. Instead of giving the full form, I give you the term of a residual vector. So here we're only using the residual vector, not using the original objective function. So 100 times x1 minus x2 square, and it should be 10 times the things. All right. So now we can actually import the scipy.optimize, import the least square library, and giving a initial guess of the solution is 2 and 2, which is x naught equal to x0 equal to 2, x1 equals to 2, or x1 equal to 2, or x2 equal to 2. We simply solve a standard least square problem, and I'm going to call this least squares function using the function we just defined, using the initial solution I provide. And here, the method we have actually 3 different methods to solve this least square problem. First is the Levenberg-McGuire algorithm. The other one is the trust region algorithm. And the third one is so-called dog box. It's basically solving the, it's exactly like the extension of the Levenberg-McGuire method, as solving the conjugate gradient step in the first step, and then using a Newton's method on the second step, and then what we call the dog-like type of approach. However, using the dog box is using a square trust region instead of a circle trust region. We'll explain that in a little bit in an example. Okay, we know that this function, we're going to print out the optimal solution for solving this is 1 and 1, cost is 0, and optimality is 0, so we converge successfully. So this is a very simple, straightforward way to solving finding a minimization problem using the least square algorithm. Instead of using the original objective function, we're using the residual vector. Second is now we contain this variable. We're trying to give a constraint. For this case, we want to provide a Jacobian information, and also we would like to have x1 is greater than or equals to 1.5, and x0, which is unconstrained still. So I'll show you how to utilize the bound definition. All right, so on top of defining the so-called residual vectors for the Rosenbrock, we define the Jacobian matrix for the Rosenbrock function as well. And we call it just Jacobian Rosenbrock right here. Okay, as return a 2x2 array is 0 times -20 times x1, and 0 and -1 as we presented right here. Again, we're using the least square subroutine to store the result into result2, using the Rosenbrock function residual vector, initial guesses, and also the Jacobian Jacobian information for Rosenbrock. Okay. And then the method I'm changing to the dog box and method is, like I said, the trust region method using the dog-leg conjugate gradient first iteration and the Newton second iteration, and combine the direction for both and becoming a zigzag dog-leg type of a shape of progress. And the box means is a box constraint, meaning the trust region is a square, is a lower and upper bound. So you have a variable based on certain lower and upper bound. And also for these dog box method, you can specify the bounds on the solution. So you have a simple constraint you can impose. For example, for the x0 or x1, I have from negative infinity to positive infinity. For x2, the lower bound is 1.5, and the upper bound is also infinity, positive infinity. So if I have a specific bounds for upper bound for x1 and x2, I can have another tuple right here. For example, I can have like this. I'm sorry. Can have like 10 by 10 instead of non-pi infinity. So 10 by 10 means x1 and x2 both have an upper bound of 10 and 10. So you can specify that by specifying np.infinity, meaning both of for both variable, their upper bound is positive infinity. So there is no constraint on those two variable on the upper bound. Once we solve it, we'll get a solution of 2 and 1.5 as we expected. x2 has to be greater than or equal to 1.5. And the cost will be 3.25, and is getting the optimal solution. So the optimality is equal to 0. So this is a very two very simple demonstration for how to using a least square model and finding the minimum of a objective function in that sense, with and without constraint. The implementation from the scipy.optimize for the Levenberg-McGuire algorithm, the method LM, and cannot handle any constraint. However, the DocBox can, and so I just want you to notice that. And trust region algorithm also can. And all right, so here we finished the part with finding the minimum of a objective function. The second application is using least square model to solve a system of nonlinear equation or linear equation. What we're testing right here is a so-called Boyden tri-diagonal vector value function, and is of 100,000 variables. So here we have a sparse system, which means the system of a nonlinear equation has its constraint matrix, actually coefficient matrix, actually is a sparse system. But we have a total 100,000 variables. And what is this Boyden function? We call it Boyden tri-diagonal function. This function looks like this, okay? It's 3 minus alpha times x, xi times xi, minus xi minus 1, and minus 2 times xi plus 1 plus beta, okay? So the solution here, we have the first, for the minimization, where x0 and xn plus 1 equals to 0. And we want to find out the optimal value for f transpose times f equal to 0. Okay? And the starting solution I'm giving is -1 all the way across for all that 100,000 variable to begin with. And this equation can be generalized in this format. And 3 plus alpha times x1 times x1 minus 2x2 plus beta, and then keep going for any particular I from 1 to n plus 1 is negative x1, xi minus 1, plus 3 plus alpha I xi times xi minus 2xi plus 1 plus beta. And the final one is just there's no n plus 1 terms in this case. The version we're going to solve, this is a general form, so the version we're going to solve is for alpha equals to -1, beta equals to 1, so the function can be represented in this format. So the Boyden tridiagonal function, and this function also only have we call the tridiagonal matrix, which means that other than the diagonal elements has value, the one position, so I minus 1 and I plus 1 diagonal also have value. It's kind of banded matrix. Okay, only have elements on the diagonal and off diagonal. One rank has non-zero element, and the rest of the matrices are 0. So if I store the entire matrices into a regular dense matrix or NumPy array, it will have 100,000 times 100,000. There's quite a bit of memory to handle. So here what we're trying to do is we're trying to using a sparse matrix to store only the non-zero elements. So here we're trying to use is import the scipy function, the sparse subroutine, to using LIL matrix is a sparse matrix. So the second, we're going to define the so-called Jacobians of these sparse matrix. So trying to find the Jacobian matrix for this Boyden tridiagonal function. The tridiagonal function for the for Jacobian matrix is also a tridiagonal matrix. And the diagonal elements are all -1. One to the left diagonal band is -1. One to the right is -2. So I'm using this as my sparse matrix to store. We store in this matrix, sparse matrix called sparsity. And sparsity is sparse matrix with n by n, which is 100,000 times 100,000. And the type we use is integer, short integer, 32-bit integer. All right. So after we define the Jacobian matrix for the Boyden tridiagonal function, first we define the main program. The n dimension equals to 100,000. Initial solution I'm going to give is start with a -1, so it's negative times n pi 1 for a vector of 100,000. We quickly solve this problem using the least square, providing the function definition of Boyden, function Boyden, providing the initial solution, x0 Boyden, providing the Jacobian sparsity matrix is called sparsity Boyden to the order of n. So this is this function we defined right here. Easily solve and solve for the solution. We can see the result of the cost is almost 0 because it's 10 to 4.5 to the -23rd, and optimality is also 10 to the 11, 1.2 to the 10 to the 11, -11, I'm sorry. I can show you, also print the entire results section, and the cost, the optimality is printed here. The solution is also illustrated right here, but since they have 100,000, they just print the 3 from the beginning, the 3 at the end. Okay. It takes only 5 iterations to solve this system, so it's not too much of an effort to solve with this function. So this is the second application we can use, using either dense or a sparse system for solving a system of linear or nonlinear equation using a least square model. All right. The third application I would like to introduce is a little bit involved, but actually is fairly interesting. And that is also the original intent for the least square model. What we're trying to solve is a curve fitting problem and using a so-called robust loss function. And what we're trying to do is basically a nonlinear regression problem. And here we have the function of the model. The model assumption is the y equals to a plus b times the exponential to the c times t. So here we have three parameters to estimate in the regression sense. The first parameter is the intercept. Second parameter is the multiplier. The third parameter, c, is the exponential coefficient. And the t is the so-called predictor variable, which means the independent variable in many sense. And y is the dependent variable. So t is my input, y is my output. I'm trying to find out if y and t has any relationship. Can be described by these three parameters a, b, and c. Okay. So to solve this, we need some of a so-called randomly generated data. So here we're using this exact equation to generate some noisy data. I'm using the NumPy random library to generate a, we'll call it, create a function to generate random data. This data take in the input of t, a, b, and the noise, and the outlier, and specific random c. Okay. The first line initialize the random c. The second line is exactly the equation number 7, how to calculate the y based on a, b, and c with the t involved. The next what we're trying to do is we're trying to create some errors or noises. The basic based on the noises times the standard normal random variables, and using the size of the t. T is the my current independent variable. Okay, so then I create a certain random integer and put it into outlier. So based on number of outlier I specify. By default is 0 outlier. By default is no noise. So these two actually don't use. Okay, so for these outlier, I'm going to multiply their magnitude by 10 in that sense. So for those outliers in the data, I'm going to multiply their noises by 10 times. And then we return the y plus the error terms and as part of the random data generated. So this is a very simple and sweet short subroutine to calculate the initial random data with or without noises, with or without outlier. Next, we're going to put it in some of the initial models solution, A, B, C, and T-min and T-max. So A equals to 0.5 to begin with, and B equals to 2, and C equals to -1, and T, my X value, so independent variables between 0 and 10. Number of points, initially I have 15. 15 data point. Okay. The purpose of this is trying to using the 15 point of T, okay, to estimate how close to the Y. So assuming I have a set of X and Y, can we find a curve described by equation 7 and how close this curve supposed to be based on changing the value of A, B, and C? Okay. So here what we're trying to do is based on this system parameter, I'm creating a training set of x and y, training set of a t, or training is linearly spaced between 0 to 10, number of points, which is 15. And we're using that to the t trend to generate the data for possible y. Okay, but this in the real world, this could be your x and y observed by a specific experiments or simulations or other sampling observation. So we're using these as a training of our model. All right. Then we create our so-called receiver function. The receiver functions is actually fairly simple, x, t, and y. And x is the one we're trying to figure it out. Basically is the function of evaluation of a plus b times e to the c times t minus y. So we want to calculate the variances of it. And the least square is trying to minimize the square of this term of a receiver function. So here what we have, x, since x is my intended solution, x equal to a, b, and c. Okay, a, b, and c are the coefficient for this regression. So they have their own, also they have their initial guesses. Based on that, I can define the so-called my receiver function in Python using input of x, t, and y. Okay, here remember x is a, b, and c. Okay, so x0, x1, x2 represent a, b, and c here. T is actually my independent variable. And y is the y observation, which is the dependent variable. Initially, I'm giving these solution x naught equals to 1, 1, 0, which means, okay, x equal to 1, 1, 0. And now I'm trying to solve the problem using the least square method. So first we compute a standard least square solution, and the standard least square solution is fairly simple using the receiver function we just defined it, which is f of x minus y, basically, just like we specify in equation 7. And initial solution is 1, 1, 0 in this case. And the argument we use is using the x trend and y trend in this case as input to trend. Okay, so we get a solution and we save that to so-called receiver of a least square, standard least square. Now we're trying to compute two solutions using two different type of loss function. See how robust they are to this outlier. Remember, in the beginning when we generate y trend we're using the noise of 0.1, and we have a 3 outlier in my example. So using noise is 0.1 and the outlier have 3. And I want to using two other type of a robust loss function to see how we handling these 3 outlier. This is the list of option to handle the loss function. First is the linear. Linear is, by default is the standard least square problem. Second is so-called soft L1 loss function. Okay. I'm using 2 times the square root of 1 plus z, whatever z is, okay? Minus 1. Z could be the objective function value we're trying to minimize. Okay, and also I'm going to try the Cauchy method is the log of 1 plus z. Okay. So we're solving two different least square model, one using the soft L1 loss function, the other one is the Cauchy function. Okay, and we applied the F scale equals to 0.1, which means the inlier procedure should be not exist 0.1 of the average data. So I can increase this, actually including more outlier, decrease this is more point becomes an outlier in that sense. So the noise level used, we'll call it F scale, which is I'm using 10%, basically the data. Okay, so we solve these two other model, in this case, using two different loss function. Okay. So now we're going to see how well each one of the models. Here we're solving three models. One is the standard least square method using the linear loss function. Second one, we're going to using the soft L1 models. Okay. Third one, we're going to use the Cauchy method loss function. So what we do is we now fitting three models we put into my solution. Here we're going to create a test function, see our test data, work on this model fitted. Again, I'm going to using the linear space between 0 to 10, number of point, which is 15 times 10. So here I have about 150 data point for the testing purpose. We're going to generate the true data, which is Y true, which is the data from using the generated data. Notice here we have no noise, no outliers, and so on and so forth. So these are directly plugged in to calculate with this equation. Okay, so no outlier, no noises level. Okay, also I'm going to generate data respect to using the T and procedure getting from ABC, getting from the first standard least squares model. Okay, using their solution. Remember the X right here, the residual least square dot X. X is basically A, B, and C, the optimal solution for A, B, and C for this model. Also, I'm using the optimal solution for soft L1 model to generate the predicted data. So Y least square, Y soft L1, and the predicted model also for the third one, Cauchy method. So we call it Y log, basically. Okay, so here is we're using each one, this optimal solution for each one of the model and trying to come up with the predicted data. So we have a Y true, which is directly calculated based on the equation. Second one is based on the once again, A, B, C are defined initially over here, and those are the true parameter I use to generate the random data, okay, to train the model. But after the data as an input, we could have a different A, B, and C optimal solution based on the model outcome. Then I'm going to plot them all, and basically the black line is true X. So the data point in the blue, okay, and the black line represent the truths, and orange line represents the linear loss, okay, and the green line and the red line almost overlap. They represent the soft L1 loss and the Cauchy loss. So you can see that actually these soft L1 loss function and the Cauchy loss function basically ignore the three outlier. And the linear loss functions, which is a standard least square method, and has impact based on the outlier, those. So we can see how if let's continue, and we show you another example about this using a different robust loss function. I'm using this article written by an author and sharing with you. The original objective function in general form can be as the yi equals to the phi of t and x plus a error term called epsilon. Okay, epsilon. Equation 8. And my least square model in trying to estimate is trying to minimize over x. X is basically the parameter we're trying to estimate. And t is, again, is the independent variable. And y is the dependent variable. And trying to find for all the observation from 1 to n, the functional value, predicted value, minus the observed value of yi squared. So this is a very standard so-called regression or so-called least square models. And the residual epsilon is a assuming to be a normal random number. So the first one we can do is using a standard one, so it's a minus xi squared, and that will be the linear portion. Okay. And we can also using a though function. Though function is a specific functional transform for this square term, the residual square term. So here we have a linear ones we talked about before, Haber loss function, and smooth L, a soft L1 function, Cauchy functions, and arctangent function. Okay, so we're going to do another example for you, since this is a fairly detail involved within scipy least square model, and for regression or nonlinear regression type of a situation. I'm going to create a graph so you can see what is the, for each type of function, how they looks like. So we plotted with a so-called R respect to the though function. We defined it here. Okay, though function, we define it. Loss function, we define it here. It looks like the linears go in this direction. Haber, this is Haber. Green is the soft 11, and Cauchy is the red, and the arctangent is the purple. Very similar problem we have, but this time we're using a more elaborated method. Is actually we're trying to calculate a and the though and sine of omega t. Okay. Okay, sorry. The a times e to the negative sigma times t is this, times the sine of omega t. So here we have a 3 parameter to estimate a. First is a, next is a sigma, third is the omega. We do the same thing called generate data using the t, which is independent variable, a, sigma, omega. And actually it was the x vectors we have used, but here we explicitly list them out. Noise level, default 0, outlier, default 0, and still the random state, I'm using the random C101. Okay, First, we can, using the functional, directly calculate y by input of a specific a, specific t, specific sigma, specific omega based on the equation 15. Then I'm going to adding a random noise based on the specific percentage of the noise, the magnitude of the noise, I'm sorry, and the number of outlier we want. Finally, we try to, for those outlier, whichever their variation basically, the magnitude of variation is 35 times larger than the regular data noise. So y plus arrow becomes the noisy output. Okay. Here is we're using a equals to 2, sigma equals to 0.1, omega equals to 0.1 times 2 pi as model generator to begin with. So here I'm going to calculate the x true data, which is the original x we're using to generate the data. Noise level 10%, T min and T max equals to 0 to 30. First, we establish the training data used to fit the models, and here we have T is linearly spaced between 0 to 30, total 30 data point. And Y trend is a noisy data we're trying to create using the T trend, which is the independent data between 0 to 30, and using the specified that A equals to 2, sigma equal to 0.1, omega equals to 0.1 times 2 pi. Noise level 10%, outlier 4 outlier, okay? Here we can, similar to before, we're using the residual function definition equals to f of x minus y as well. And I'm going to using the initial guesses x not equals to 1 for all the estimate. Import the least square library, solving a standard linear least square model with a linear loss function. This is the most straightforward one as a baseline. Using the residual function, x naught is the initial solution, and t trend and y trend as the input data to train. Next, we're going to do is we're using soft 11 and the Cauchy with F scale. F scale again is the inlier data, which is 30% of the noises. Okay, so so solving two model, one is robust, one is robust 2, one using the soft L1, and the other one we're using Cauchy again. We did this before. Same thing, we're going to do create a test data, okay, to verify my result, verify my model, using the linear space between 0 to 30, total 300 data point. I'm going to generate data using the t-test. Okay, t-test is the verification data with the A and sigma and omega originally defined with no noise level, no outlier. So that's a true functional evaluation directly from the model. The next, I calculate so-called predicted data from 3 different models. We're going to generate data using the A, sigma, and omega value getting from the solution for these 3 models. So this is Y predicted for standard linear square. This is Y predicted for this using the soft L1 loss function. This is Y predicted using the Cauchy mod loss function. easily plot those three, all these. The original data you can see in the blue dot and have a couple outlier. And using the true data, which is the orange portion, and the standard least square, which is the green line. Okay. And solve L1 and the Cauchy least square model actually provides very close result, and by ignoring some of the outlier here, 1, 2, 3, 4, basically. Okay, so even for the large outlier, but in the beginning, the linear loss function actually skewed by the outlier. However, the soft L1 and the Cauchy method actually is very robust in terms of outlier impact. Okay, I'm going to skip this portion. I'm going to give you another example for finding the minima of a we'll call a permanent 0D beta function. And this function was provided in your final exam, and we're trying to see if we can find the minima using the least square model. And the question in the final exam are different than here, so we trying to give you a different perspective on how to solve the minimum. All right, so we're trying to plot this function first, okay, and give you the f and the first derivative based on the equation we get. Okay, this is a perm data, okay. And then we're going to plot this function. It looks like this. It's not a convex function because it's a level set. Contour is not a so-called epigraph is not a convex set. So here we're trying to do is we're trying to using least square method to solve this function as well. So instead of put it in the original objective function, we're trying to put it in as a residual function. See, notice that the objective function for this beta function is also sum of the two square term, okay? So we can easily create a residual function for the first term and the second term, okay? So the beta f is actually, I'm not returning the functional value itself, I'm returning a vector of two elements as a residual for the first term and the second term. Instead of calculate the first derivative for original objective function, we're using the Jacobian matrix. And the Jacobian matrix is much simpler to calculate based on the first term and the second term. It's 11, 12, 22 times x1, and 24 times x2. So this is a fairly straightforward. We did it. All right. So I'm trying to solve for this residual function, which is sum of the square of the first term and the second term on the beta f function. Initial guess is 2.0 and 0, which is the initial guess for the solution, solving for the least square. Okay. I'm using the Levenberg and Maguire function and find the solutions 1 and 1/2, which is originally we did it for this function. And printed out the result is successfully finding solution using 148 functional evaluation, 145 Jacobian evaluation, and optimal solution is equals to 10 to the minus 7. Similar like before, we're using a Jacobian data, okay, and using the dot box function and giving the upper bound, lower bound for the solution, which is none, but I still keep the same. For using the DocBox trust region method, which is we are able to solve this whole thing only in 7 iterations, okay, using 7 functional evaluations, 7 Jacobian evaluation in that case, and getting this very similar result. And okay, 1 and 1/2 is my optimal solution. So the optimal solution is usually 1 and 1/2, 0.5, 1 and 0.5 is my optimal solution in this case. All right, this is pretty much summing up our this lectures on least square model. We show you 3 different type of application. First is finding the minima of a objective function using least square model. Second one is you solving a system of nonlinear equation or linear equation using least square model. Also, the third one, which is the original intent for the least square model, is solving a so-called curve fitting, nonlinear curve fitting models for using the least square models as well. It happens to be this the 3 particular method. First is the Levenberg-Maguire method without constraint. The second one is a DocBox method with the bounded constraints on the variables. And the trust region algorithm we haven't introduced for you. And trust region method is the default linear. If you didn't specify which method you are using, and they by default, for example, these 2 models we try in the curve fitting, we didn't specify what method we're using, and by default they are using the trust region Newton's conjugate gradient method, so basically. As using conjugate gradient linear approximation of the gradients and using that as a solver. So we basically show you 3 different methods. First is the Levenberg-Maguire method. Second is the DocBox method, and by default is using the trust region conjugate gradient method. Okay, this pretty much summing up the this lectures of using the least square model to solve various application. So this concludes this lecture. We see you in the next lecture video. Bye-bye.